Hey there, we're going to go over some horizontal projectile motion notes. Now, there's two things that really classify an object to be in horizontal projectile motion. And the first one is that the object has an initial horizontal velocity. The other is that the object is in free fall. And if this is the case, then that object is moving in a horizontal projectile motion. An example of this is, let's say I have a table and there's a ball that's rolling, so it's initially moving horizontal, and then it rolls off the table, and then it's going to be in free fall after that. So that's a horizontal projectile motion. An example of it not being horizontal projectile motion would be a skydiver, right? Because a skydiver has other forces other than force of gravity. Now, remember from the last video, in order for it to be in free fall, the only force is gravity. Another example of an object that's not in horizontal projectile motion would be an airplane, right? Because the airplane also has a drag force or air resistance and a thrust force with the engine, so it's not in a horizontal projectile motion. So let's kind of draw out an object rolling off of a table. So here's the table, and this object is rolling horizontally, and then it falls. So let's kind of look at some snapshots as it's falling off this table. So probably right around there, here, and then we'll hit the ground. And so if we go in and we draw some velocity vectors for this object, so we'll call this Vx. If I look, there's no vertical velocity to begin with. Okay, it's only moving horizontally. And right about here, you still have this horizontal velocity, but now you have a vertical velocity. And let's also draw a free body diagram of this ball that's rolling and falling off the table. Once it falls off the table, the only force that we have is going to be Fg. Okay, so there's nothing that's pushing this thing through the air, so there's no horizontal forces. And if you remember back in our forces unit, if there's no forces, in terms of motion, that means that is moving at a constant velocity. So horizontally speaking, this ball is moving at a constant velocity because there's no horizontal forces. But there is a vertical force there, and that vertical force is your force of gravity. So just like in a free fall, the acceleration vertically, so we'll put a y, is just going to equal g, or 10 meters per second squared. So in essence, it's really just a free fall problem vertically, and then horizontally speaking, we're moving at a constant velocity. So if we kept drawing these velocity vectors, because it's moving at a constant velocity horizontally, then they would all be the same size. You'd have the Vx here, and then we'd have a Vx here, all the same size. But because we're accelerating vertically, that vector would get larger and larger vertically because it's accelerating vertically. So this object, it's accelerating down, and then it's moving forward at a constant velocity. So that kind of describes the motion of an object that is in this horizontal projectile motion. Now, what you can see there is we have two directions of motion. We have a horizontal and then we have a vertical direction. And the key thing here is that they are independent of each other. Oops. So in other words, your vertical, or I'm sorry, your horizontal velocity, it doesn't affect the vertical velocity. Okay, they're independent of each other. And excuse me, when we solve a horizontal projectile motion problem, it's beneficial to make yourself a table. Okay, so you got your x and you got your y direction. Now remember, we talked about these 5 different variables we have. That's the same case here, but we're going to have it for the horizontal side and for the vertical side. So in other words, we would have a delta x and then we'd have a delta y. We'd have an acceleration in the x direction, we'd have an acceleration in the y direction. We'd have initial vertical velocity and an initial horizontal velocity. We can have a final horizontal and a final vertical. And we have time, but the time here, this right here is my bridge to connect these two independent directions of motion, because the time is going to be the same for both the horizontal and the vertical directions. So a lot of times what happens with the horizontal projectile motion problem is you'll be given enough information to solve on one side or the other for your time, and then you can plug your time in on the other side and solve for whatever it is that the problem is wanting you to solve for. Now, there's 3 things in here that are always going to be the case. And in the y direction, we know that, like we said over here, initially there's no vertical velocity. So on a horizontal projectile motion, your initial velocity in the y direction, that should have been a y there, is always going to equal 0. And we said vertically speaking, it's just a free fall problem. So that means that your acceleration is always going to equal 10 meters per second squared. And then the other piece of information that's always the case for this horizontal projectile motion problems is your acceleration in the x direction. Remember, we said that our forces were balanced in the x direction and it's moving at a constant velocity. And since it's a constant velocity, that means your acceleration is going to equal 0. So the problem won't state these things, but you just need to understand the concepts behind it. That you're vertically speaking, your acceleration is always 10, your initial velocity is 0, and horizontally speaking, your acceleration is always equal to 0. So let's kind of look and solve a problem together and see how we would do that. So this one says we have a ball that's rolling across a 1.2 meter table. It has a velocity of 4 meters per second. So this would be your horizontal velocity. And then it falls off. And we're asked to find how far away from the table the ball is going to land. So let's draw a picture so we can kind of visualize this. We have our table here. Here's the ball. It has an initial velocity of 4 meters per second. And they gave me the height of my table. It's 1.2 meters. And this ball, it's going to fall off, land over here, and that's what we're trying to solve for. We're trying to solve for this horizontal distance from the table that it's going to land. So we said we'll make a table. Let's go ahead and draw out our table for with the x and the y direction. And let's go ahead and write down all of our given information. So we know that our um, Vx, the initial velocity in x direction, is equal to 4 meters per second. And then we also know that our height of our table is going to be 1.2 meters. And then we got to go back and think of those three things that we said is always the case for an object that's moving in a horizontal projectile motion. So horizontally speaking, we know our acceleration is going to equal 0. Vertically speaking, we know our acceleration is going to equal 10 meters per second squared. And then also, vertically speaking, we know that the initial velocity was equal to 0. So there's our given information, and then let's write down our unknown, what we're solving for. We're trying to solve for our delta x. And looking at the two sides, we have three pieces of information on our vertical side. So we're going to start by solving on our vertical side. And what we're going to solve for is going to be that bridge that we talked about, which was our time. Because the time on the y direction is going to be the same on the x direction. So on the vertical side, the one variable that we don't care about is going to be our final velocity. Okay, so we don't care about our final velocity there in the y direction. And the kinematic equation that we could use to solve for the time, the one that doesn't involve the final velocity, is going to be delta y is equal to v naught t plus 1/2 at squared. So we're going to solve for time using this information here in the y direction. Now, the initial velocity was 0, so that means this is all going to just cancel out. So I'm left with delta y is equal to 1/2 at squared. We're solving for time, so let's multiply both sides by 2 to cancel that out. Let's divide by our acceleration. And to get rid of that squared there, we'll get the square root. So the time is going to equal the square root of 2 delta y all over a. Now we can substitute and solve. So 2, and our delta y there was 1.2 divided by 10. And when you plug that in, you should get 0.49 seconds. So that 0.49 seconds, we'll go ahead and fill that in our table. And when we do that, it's going to go on both the x and y side. 0.49 seconds, 0.49 seconds. Okay, remember time is kind of our bridge there. So there's kind of step one in solving the problem. Now we can solve what they really wanted, and that was your delta x. Because now we have three pieces of information there on the x side of our table. And so again, we don't care about our Vx here. So we're going to use the same equation. So delta x is going to equal V naught t plus 1/2 at squared. And now my acceleration is equal to 0, so all of this is going to cancel out. So your displacement is just going to equal the initial velocity, horizontal velocity, which was 4 meters per second, multiplied by the time, which we just solved for, 0.49 seconds. So your seconds cancel, and your horizontal displacement is going to equal 1.96 meters. So again, on these problems, most of the time, you're going to end up solving for time, and then you plug in the time for the other side, and then you can solve for what they want. So with so many variables here, it's really important to make yourself a table and organize all your data. Write down what's given. Remember the three things that are always the case for a horizontal projectile motion, and then you can start solving. Now, lastly, we'll look at another example here of two situations. Okay, so let's say we have another ball that is rolling off the table, but I also have one, same size ball, same mass, and I'm just going to drop it. And the question here is which one hits the ground first? Well, let's kind of take a look. We're trying to see which one is going to hit the ground first. So what we're interested in is the information in the y direction. Because remember, the x and y direction, they're independent of each other. And for both cases, your initial velocity in the y direction is equal to 0. In both cases, your acceleration is just equal to g. And in both cases, your delta y, in other words, how far it's falling, is the same. So knowing this here, that means that they're going to hit the ground at the same time. So key thing here is remembering that the horizontal information here is completely independent of our vertical information.